I think I'm live now. Can anyone confirm if audio, video, etc. looks fine before we get started? Today's discussion would be quick because I solved only 4 problems. Like people in the chat, like how many problems were you guys able to solve today? That will give me some rough estimate on like which problems to focus more for. Hello, hello. Like is audio, video? Am I audible? Okay, thanks, Death Cruiser. Thing so I was asking like people in the chat like how many problems were you guys able to solve today? Like I solved the first 4 problems, so like probably today's discussion would be quick. Like the tempo is high, so that's where we are. Like I will probably look at solutions of D2. If I understand them, I will end up sharing it. Otherwise, we will just discuss A, B, C, and D. Mhm. So that's where we are. Yes, like the contest was hard, and in fact, it was expected. Like if you look at the problems score, like D2 should be considered some of these two, not the other one. So this is 3000, this is 3000, this is 2500. So these 3 parts were expected to be hard than what we have regularly. So that's where we are. So I think I will get started now. So first problem says let's introduce the two-player game. Table tennis where a winner is always decided and draws are impossible. 3 players, Sosoi, Fofoi, and Hooi, want to spend the rest of their lives playing table tennis. They decide to play forever in the following ways. In each match, 2 players competed with the third spectator. To ensure fairness, no player can play 3 times in a row. The player who plays twice in a row must sit out as a spectator in the next match, which will be played by other 2 players. Otherwise, the winner and spectator will play the next match, and while loser will spectate. Now, the players fully immense in infinite loop of matches have tasked you with the following problem. Given an integer k, determine whether a spectator of the first match can be a spectator of the kth match. So, what the problem statement says is like we have 3 people, let's say A, B, and C. We have 3 folks. A, B, and C. Let's say the first match is played by A and B. And it says, let's suppose like A wins this match. And like let's say P1 and spectator C. Let's suppose A wins this match. So the next match would be between A, B, and C. Sorry, A, C, and B. Now, no matter who wins, because A has played 2 consecutive matches in one time, he has to sit out. So, like now, the next match can only be between B and C. Doesn't matter who wins. If A wins, C moves out. If C wins, then also C remains here. Now, if you see, like C has played 2 continuous matches here, so we have no choice but to play a match between like C will have to move out and play a match between B, A, and C here. Now, if you see, B has played 2 matches right now. No, doesn't matter who wins this match. The next match, like B will have to move out and C will come in their place. And if you keep trying it, you will notice that the cycle starts repeating here. The set of folks who are here as well. And similarly here as well, we don't have any choice. A has played 2 matches in a row, so B must come its place. Now C has played 2 matches, so A must come at C's place. And basically we are at the same place where we started. So essentially the idea is, after 2 matches are played, we will be forced to have next games would be forced. We will not have any choice who to choose or not, because we have 3 players, and if we say, let's say we have 2 matches, M1 and M2, then one player must repeat between these 2 games. There will be a repetition. And then in the next game, these 2 guys must come and fill in the places here. And in that case, this player will start repeating and so on. So the idea is the set of players who play first game would be the set of players who will play the 4th game, and the same set of people will play the 7th game and so on. So the problem reduces to checking whether and when if you take a reminder by 3 gives 1 as a reminder or not. And essentially this was the solution for this problem. And when taken reminder with 3 gives 1, print yes, otherwise no. Any questions, anyone? Any questions, anyone on the first one? Okay, first one is okay, looks fine. Okay, then let's move to the second problem then. Perfecto. A permutation of length n is perfect if for each index I, it satisfies following. The sum of first I elements is not a perfect square. Perfect squares are the numbers 4, 9, 25, 36, and so on. You would like things to be perfect. Given a positive integer n, find a perfect permutation of length n or print -1 if none exists. Okay, so essentially this is the problem statement. It says we have to find a rearrangement of 1 to n such that any prefix sum is not a perfect square. Okay, first case is when n is equal to 1. You don't have any choice, your p will be equal to 1. And sum of this is always 1 is a perfect square because 1 multiplied by 1 is 2. And that's why the answer here is -1. Now let's say we will print this 1, 2, 3, 4, and sum of all the n numbers is also fixed. And it doesn't matter how you arrange the values, this sum will always be fixed. So if this is also a perfect square, then we should print -1. Any questions, anyone? These are the 2 cases when you will definitely have -1. N equal to 1, you don't have any choice, so that's a -1. 1 is a perfect square. And if sum of all the numbers is a perfect square, then we don't really have any choice. Doesn't matter how we rearrange the number, sum of all the numbers would be equal to the required sum we had, and that's a perfect square. And then my claim is this is the only case when we will have impossible. Otherwise, let's say sum of all the numbers is not equal to perfect square. Then the idea is we will print 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so on. Let's say we print these numbers. Now let's say in this sequence this is a perfect square. Let's suppose that's not necessary. Let's say this is a perfect square. If I check and if I find this as a perfect square, what I will do is I will just swap these two numbers. Now this sum will be equal to perfect square plus 1. And we know that there are no two consecutive perfect squares, and we will keep doing it. Like basically we will create an array of 1 to n where ith element is I. Then we will keep taking sum of the first I elements. Whenever we find a perfect square, we replace it with the next element, so that total sum so far becomes plus 1 here. And we keep doing it this way. And because we know that the sum of all the numbers is not equal to perfect square, so we will not need such rearrangement for the last element. And essentially this was the solution here. First, I have a method function which gives true or false if a number is a perfect square. The idea was to take the square root of here and like basically just find the integer component and check L star L equal to K. Now, if sum of all the numbers is a perfect square, print -1. Otherwise, just print numbers from 1 to I. If the sum of first I element is perfect square, then remove that number and swap it with the next element. And then keep printing it. And essentially, this is the idea. So, like, proof is for me or like someone in the chat only. Like, this was the main idea. And like, the main idea was like, if I'm printing numbers like this and if everything is consecutive, if I swap two numbers, the prefix sum only increases by 1. And we know that there are no two consecutive perfect squares. Okay, so we have this function which checks if something is a perfect square or not, which takes k square root of k and like basically trying to find the nearest integer which is less than k. So if the sum of all the n numbers is a perfect square, -1, we don't really have any choice there. Otherwise, for each I, just keep maintaining the running sum. If you find perfect square anywhere, just swap it with the next element. And you keep doing it. And because sum of all the numbers is not a perfect square, you will not need such swap when I is equal to n-1. And essentially, this was the idea. Any questions, anyone? Like, is this the only way? Like, people can have more different ways. Like, there is a good chance if you print random elements, then also you will get it. Like, let's try it. Let's just check if the given array is valid or not. We are not doing any swaps here. If there is a square, perfect square is valid is false. If the array remains valid, you break. Otherwise, you do random shuffle. And there is a good chance even this solution will get an AC here. Okay, system testing is going on. We will try this idea after we are done with the fourth problem. Like you can find solutions later on my YouTube channel. So I think we will try this idea after system testing ends. So and I will probably move to problem C. Any questions, anyone? Okay, let's move to problem C. No, like it's not necessary the answer is -1 only for one. Like there were 6 examples when I tried it locally. So there are only 6 test cases where the answer is -1. N equal to 1 is one of them. Like for example, n equal to 8 also you will have -1. Like sum of first 8 numbers is 36. That is also a perfect square. If s is a square, then s plus 1 and s minus 1 is not. That holds true only when s is greater than 1. Like 0 is a perfect square, 1 is a perfect square. But nothing apart from them. You won't find any two continuous perfect square apart from them. In an Italian village, a hungry mouse starts at vertex st on a given tree with n vertices. Given a permutation p of length n, there are n steps. For the ith step, a tempting piece of Parmesan cheese appears at vertex pi. If the mouse is currently at vertex pi, it will stay there and enjoy the movement. Otherwise, it will move along the simple path to vertex pi by one edge. Your task is to find a permutation so that after all steps, the mouse inevitably ends at vertex en where a trap awaits. Note that mouse must arrive at en after n steps, so it may pass through en earlier process as well. So, like the idea here is so like the problem. Let's understand the problem statement. It says we have a graph or a tree, in fact. Let's say the mouse is initially at root, and we want to end at root as well. Like basically, the problem statement is you have mouse somewhere, let's say here. Now you choose one vertex, then the mouse will move, take one step towards that. So, for example, mouse came here. Now, let's say you called out this vertex, then the mouse will move one step towards it, let's say here. Then you called out this vertex, then the mouse will remain here only. So, basically, the idea is mouse is somewhere. You call out some vertex, then the mouse will move towards that vertex. But if you call out the same vertex where the mouse is, then mouse will remain there only. Our goal is like where is st? Okay, it's given that mouse is at a place starting vertex and the final tap vertex where we want to be. Let's say both the vertices are same. You start at some vertex, you have to call all the vertices and you want to remain at the same place after that. Then what will be your idea? Like any ideas, anyone? Okay, didn't get the question. Like I think I can take one of the examples. Let's take fourth example. 1, 2, 3, 4. We have this graph. 1, 2, 1, 3, 1, 4, 4, 5, 4, 6. Initially, we have a mouse which is here. Let's say we have a person here. Like we have to call, like we have to basically direct mouse to at every place, and at last we want mouse to be here. Let's also look at the solution. One. So first we call out vertex number 1. And because the mouse is already at vertex 1, so mouse does not does anything here. Then we call out vertex number 4. Then the mouse will move towards vertex 4, one step this side. Now mouse is here. Now we call out vertex number 3. So mouse will take one step towards vertex 3. So in that case, mouse comes back here again. Then we call out vertex number 2. So mouse will take one more step towards vertex 2 from wherever it was. And then we call out vertex number 6. So mouse takes one step towards vertex 6. He goes back here. Then we have vertex 5. Mouse takes one more step towards vertex 5. So we reach here. And you see, like we have called all the numbers so far. And at last, mouse is at number 4. And essentially, this is the problem statement. Any questions, anyone? The idea is we have to call out all the numbers. Whenever we call a number, if mouse is at that number, mouse will remain there. Otherwise, mouse will take one step towards that number. Like it's not necessary that we have to visit all the vertices. We have to just call out all the vertices here. And even probably this is the submission, even the random solution will pass here for the problem B. Any questions, anyone on problem B before we jump on to problem C? Like where did my submissions go if it's running a system? Okay, so even basically just trying to print random values will give an AC here. No, like I will not discuss E and F. So this is the problem statement. Now coming back to solution, let's first solve a simpler problem. We have a tree where initially the mouse is at root. You have to bring the mouse back at the root. Then what will you do here? Like mouse is at root and we have to come back at the root again. Like the idea is to do a DFS here and print that node whenever we leave that node. So for example, mouse is here. Let's say initially the mouse is here. We start with DFS here. DFS from this node. We come here. We come here. Now this is the lift node, right? So when we are going back, we say mouse, try to come on this node. So like now when we are going to leave here, we call mouse this side. So mouse will come here. We go back to the node. We come here. Now when we are returning back, we call mouse to come on this node. Now when we are going back from this node, we call the mouse to come on this node. So this guy will again come back here. And we are here. Now when we go on this side, we go this side. Then we call, when we are returning here, we call mouse to come on once on this side. So now mouse will be here. And we are here back. Now when we are returning back, we ask mouse to come back to this node again. Mouse comes here. Now we go to this node. We go to this node. When we are leaving here, we ask mouse to come back. Then we go this node. And when we are returning here, we ask mouse to come on this side. And then we are leaving here. We ask mouse to come here. So mouse will remain here. And then we are back at this node. Now we will call this node because essentially we are living here. So mouse will come back here. Like essentially the idea is we run a DFS order, but whenever we are leaving a node, we will ask mouse to come towards that node. The idea is, like for example, let's say this is the route, and then you are on some path here. Like this is your DFS tree right now. Yeah, basically we return whenever we are returning, we print that number whenever we are returning from the node. The idea is if we are in the DFS here, our mouse will mostly remain somewhere here. So the idea is when you return from here, you just ask mouse to come towards this node. Or other way to put at it is, if this is my current node, then my mouse will be either here or just one node below it. So whenever I will call mouse to be here, either mouse will come from here, or if mouse is here, it will remain here, or if it's at top somewhere, it will come one step towards it. So whenever I leave this vertex from the DFS, my remaining part is this, and mouse again remains up to this area only. And that was the main idea. Like mouse will always be at a place which are your you are at node X. That mouse will either be at one of the parents of X or just one of the child of X. And essentially this was the idea I came up with. And this ends up solving the problem here. So the idea is because we want node to be at En at last, like this is the solution. When your mouse, you want mouse to be same at the starting node. But essentially the idea is like in context, what I did was like, or I think I can first explain an example. Let's say mouse is at node 1 and we want mouse to be at 1. The idea is we do a DFS here, we go to 2, we go to 3. Mouse is still at 1. Now when we are returning from here, we ask mouse to come towards 3. So 3 is our first operation. And now this mouse will come from here to here. Then in the next DFS, we will go to 4. When we are returning from 4, we ask mouse to come towards 4. So now mouse is at 4 and we came back at 2. Now we would be going back from 2. Whenever we are going back, we ask mouse to come towards 2. So mouse will again come from here to here. Then we go towards 5, DFS, standard DFS. When we are returning from 6, we ask mouse to come towards 6. So mouse will essentially end up coming towards 1. And when we are returning, now we are returning from 5, so we ask mouse to come towards 5. So from here to here, mouse will come here. And we are back to 1. We go to 7 then. We go to 8 then. When we are returning from 8, we ask mouse to come towards 8. So mouse will even come from 8 to 1. When we are returning from here, we ask mouse to come towards 7. So mouse will come from here to here. And when we are at 1, at last we will call 1 as well. So mouse will come back to 1 again. And essentially this was the idea. This solves for the case when your starting and ending node is same. And I have a hunch like this solution should also work if starting and ending nodes are not different. Although in contrast I did something different, but let's see. Let's just start DFS from the ending node. Like we don't really care about what starting node is. Like let me just write, and I think I will also share what I ended up doing in the contest, which was based on my previous idea. Yeah, like, and in contrast, what I did was to build upon this idea. Like let's say this is the starting node, and then this is the path. And then each of the nodes have some nodes hanging towards them. So first I did a DFS from here. So the node is at here. I run everything here and I come back to the same node. Now I do a DFS here, similar kind of. And after this, I call that node. So after I'm done with this, the child was here. Then what I did was I did the same thing for this tree and for this node. So after processing this, the node was here. And that's how I started incrementing one after the one. That also worked. And like this is also a different idea. Like one more idea which people have in the chat is like you can find the distance of each node from En, sort them and print them in the decreasing order. And essentially that should also work here. Because whenever you are doing something, like the node is also going towards the main row. And like how did you, like I tried to play around with different permutations on how I can move around, and that's what I ended up with this solution. Like one more idea here generally is like, let's say you are allowed to keep only node 2 times or something like that. No, like E not equal to S, like the same idea works to begin with. Just root the node at E, like the ending node, and that will still work. And now you can try to prove why that works. Like essentially, the exam I had, like node will always be in path, is not true in starting, but at some point of time, the mouse will be trapped in the node from your current node up to the parent. And when that happens, like everything falls in place for all the remaining nodes you keep visiting here. And like that was the reason why the same logic for E not equal to S also works. Like the first logic I said. In contrast, what I did was I treated each node as a separate trees here. So first I did a DFS for the starting node. Then I did a DFS from the one node after the starting node. Then one node over there, but that was an overkill not required. Yeah, like it is correct if we visit AND node multiple times before the final step. In fact, this was also written in the problem statement. Yes, system testing is over. It says we must be at AND node after AND step, but we can be passed through AND nodes during earlier process as well. So this was problem C. Any questions, anyone? Afterwards, I will discuss problem D1, and I think that would mostly be it for today. Like BFS idea, like you can just print like the reverse BFS order, and that should be fine. So I will probably move to D now. Like my idea was the same idea I explained, and then one more extra step, which was not required to begin with. If you see my code, like I just removed half of my code and submitted again, it passed here. So if you are interested, you can look at the submission, but that's strictly not required. So yeah, like the main idea was if starting equal to ending works, my claim is same solution will also work if starting is some another node. Because when I was trying to prove it, I said whenever you are at some node, if starting equal to end, then your mouse will always be trapped on this path. But if starting is something else, let's say here, that assumption is initially not true. But as you keep moving like this, at one point of time, mouse will come and get trapped in this path. And once mouse is trapped in this path, like the same logic works, which I used earlier as well. And that's why doing a DFS from AND works here. Like doing DFS from AND just means we are assuming AND node is the root node. So like first I tried with mouse at the root node, and I want mouse to remain at root node. What should I do? Then what I am saying is, if you use the same algorithm, does not matter where your mouse is. At the end of that algorithm, mouse will again be at root only, even if whatever is the starting node. And that's why starting is not required here. And the main idea is like I was trying to prove like if your mouse is at this node, then your mouse is always trapped from your current node up to the parent here. But if mouse is at a random place, that will not be true in starting. But at some point of time, mouse will get trapped in this path only, and that's why this works. Any questions, anyone? I think I will move to problem D then. Okay, code. Like the idea for the code is I first take starting and ending the graph I have. Then I am doing a DFS from the ending node. And whenever I am leaving from the DFS function, I end it in my answer. And at last, I'm just printing that order here. Like do a DFS, basically when you are leaving the DFS function, print that value in your order and you should be good. Okay, I will move to problem D1 then. It says this is easy version of the problem. The difference between the version is that in this case L is equal to R. You can hack only if you have solved all the versions of this problem. For a given integer n, the first n terms of infinite binary array is given, and after that it is defined as this. Now we have to compute sum of elements from L to R. In this problem, L is equal to R. So it essentially says find one of the element which the value I am giving to you. Now this is how you play around with this value. Let's first say n is equal to odd. What happens if n is even? Add one more term with the given algorithm. And you can find that term using this value here. So now we have n equal to even, n equal to odd. Now let's say we want to find the kth value. Like so essentially what will be k here? Or like let's say we want to find some k equal to 2j plus 1. This value. So what will this be equal to? A1 XOR A2 XOR up to AJ, right? One second. Why is this an XOR? Let's say we want to find this value. Let's say we want to find akth value, which is this, right? So ak we can write as a1 XOR a2 XOR up to an, and I have said that n is equal to odd. Then I will have this an plus 1 plus an plus 2 XOR, right? And the main claim is like values will repeat. Okay, let's put it this way. Let's ignore this part. Let's say n is odd. What happens when n is even? We can add one more value by finding the next value from the series, and we just increment n by 1. Now my claim is like al is equal to al plus 1 if l is odd, even. Why this is the case? Because al is XOR of a1 up to al by 2, and al plus 1 will also be a XOR of the same value, same numbers. Any questions, anyone? Like al will be equal to al plus 1 if l is even. So basically after the n number, both the numbers will start repeating in pairs. Any questions, anyone, for this observation first? Now we have this number. Then let's say we have to find the kth element. Like for k, we will need XOR of a1 up to am, right? we need XOR of A1 up to AN, then few more terms plus AM, right? The main idea here is this value is fixed. The values will cancel out in the pairs of 2, 2 only. And at last, either AM will also be a part of pair. In that case, it would be 0. Or only AM will remain here. Like, let's look at it this way. We will have A1 up to AN in the prefix sum, plus some two values, AN plus 1 and AN plus 2. And both of these values will be equal. So if we take XOR here, this will be 0. Then we take XOR here, two values, that will also be 0. Then we take XOR here, two values, it will be 0. And then we can have AM here, which is equal to AK by 2. In that case, we know what is the XOR of these numbers. We just try to find what AK by 2 is. And then we print this multiplied by that XOR. Or alternatively, it's A1 up to AN, AN plus 1, AN plus 2. These values cancel in pair. Next two values also cancel in pair. Next two values also cancel in pair. And let's say this is the AK by 2. In that case, we don't have to even calculate anything. We know like the XOR of everything on this part will be 0. So we can just print XOR of first n numbers. Any questions, anyone? So like essentially this is the idea for this problem. Let's just take all the numbers as input. If n is even, we increment it by 1. We just increment 1 by n by 2 and try to find the next value. A dot implies back next. Now we also need XOR of all numbers. Now I have a recursive function. I need to print the value of k, right? If k less than equal to n, we know like what the kth value is. Otherwise, if k is odd, then we know that k will also be get cancelled in the pair. So we just need only the XOR of a up to n. So first we need now XOR of a up to n, right? So if m is odd, like m will get cancelled. No, let's put it this way. Now if m is less than equal to n, we have to just find XOR of first m values. Otherwise, if m is odd, then like we don't have to calculate anything. Like this is just the first n numbers. Otherwise, like m will be the pair that will still remain. So we try to get the value of mth element here. And essentially this is the solution for D1. Any questions, anyone? Like the main observation here was like after n, like values will generally start repeating in pairs of 2. So this is problem D. Any questions, anyone? I will just check some submissions for D1, D2. If those makes any sense, I will share it. If I don't understand them, I will probably end this thing now. Okay, tourist solution failed for F1. Wait, what? Why did tourist got wrong answer on test one? Is he using some randomization? Okay, looks like he's using split tree or something here. Yes, RNG. I think that's all I had. So thanks everyone. And I think I will probably leave D2 for the editorial here. So like I think I solved only people in the chat. Any questions, anyone? No, like in my code, like A is not A, like but the prefix are there. So AK and AK minus one just gives me the kth value there. So like if you look at the input function that I am converting it to prefix or value rather than this, trying to take shortcuts there. So like essentially the solution is this. You read all the numbers. If n is odd, you add one more number there. You also keep XOR of all the numbers. Now you run here and based on what value it is, you keep printing it. Yeah, like implementation is more about like coding more problems. And like that's the only way. Like try to find hard problems. You may not find it in Codeforces, then probably try add coder problems. Like earlier you used to have long challenges and those you used to do it. So thanks everyone. Like people in any questions, anyone before we wrap it up for today. Like to like basically Omnic's famous advice is to get better at X, do X. So if you feel you are not good at implementation, do read other people's solution, but definitely code your ideas. And there is no other shortcut there. Where to see your submission? Like generally, you can go to my profile. Like you can go to my profile, look at contest here. Then you can click on some like all contests. Then you can click on the solve count here. Now you will find my solutions here. Otherwise, or you can just add me as your friend here. And then like I cannot add myself as a friend, but let's where you can add me as friend here. Like I have added this guy. Then you can see friends standing here. So after the contest ends, you can look at your friends here. Double click on any submission here. Let's say this. Now you can find all of my submissions here. That can be another way. So thanks everyone for joining today. Can you suggest any topic like USA CEO guide is generally what I end up recommending folks. You can try searching here or cses.fi. Like those would be the first places I would recommend anyone to start from. And these guys also have a competitive programming handbook. You can also read this book. So thanks everyone. And that's all for today.